to inviting me here to this workshop. And I must begin with a disclaimer, although this is a CFT workshop, but I'll be talking about something in quantum field theory amplitudes. And I hope some of the contents will be of interest to people working in CFT as well. So this talk is based on some works that we have been doing for last couple of years, and also some ongoing works. So these works have already appeared with Maninder Singh, Faizan Bhatt, and Devpriya Chaudhary. Faizan has now moved to INF in Geneva, completed his PhD. Devpriya is in final year of his PhD. So let me begin by giving a broad overview and motivations behind our work. And first, I recall some basic properties of scattering amplitudes and quantum field theory, such as locality. This is a statement that interactions are localized or confined in region in space and time, and beyond these interacting regions, states can be thought of as free states or scattering states. And scattering amplitudes are functions, especially analytic functions, except at the point of the singularities. And the singularities can be of different kinds depending on, like if we do a perturbative expansions, there can be simple poles, there's branch cuts, and so on. And scattering amplitudes are usually analytic functions of the Mandelstam variables, like in the case of 4-point functions. These variables are S, D, and U. And also scattering amplitudes have certain high energy behavior, such as Regge boundedness or Prosser bounds. Prosser bounds is a statement how the cross-section of the amplitude grows with energy. And a simplest case, if we are studying identical particle scattering, then the scattering amplitudes will be crossing symmetric functions of the Mandelstam variables. So here is an example of an amplitude, which is called trace phi cube. It's a theory. So here, these scalars will be biadjoint representations of some internal group. And because of the color structure, here we can talk about partial color ordered amplitudes, which can be written on a plane, meaning the external states can be ordered in a given plane. And then we can just talk about S channel and P channel if we talk about planar ordered amplitudes. And usually in quantum field theory, we have to write down the full amplitude. We have to sum over diagrams which have singularities in S channel and also in T channel. And so this is simplest tree-level amplitude, which have only simple poles, and amplitude is actually given by this 1 by S minus m square plus 1 by T minus m square. And this is just to show that in quantum field theories, we need to add all the channels to get the full amplitude. Now we ask the following question: can we have an amplitude which satisfies all the above properties, is crossing symmetric, to be expressed only in terms of single channel diagrams? Or in other words, can we have an amplitude which satisfies this property that sum over S channel diagrams is equal to the sum over T channel diagrams, and individually they're equal to the full amplitude? And in quantum field theory, just as we saw from these examples, that in quantum field theory it is difficult to have such amplitudes. Now there are amplitudes in string theory, and in fact amplitude in string theory has some particular behavior. For example, this is what is called Venezian amplitude or Euler beta function, and this describes 4 tachyonic amplitudes. And this has a worldsheet integral form like this. The pointer. Can you see the pointer?
No, pointer is not going to work.
Okay. Okay. So anyway, so this worldsheet integral actually converges for negative values of S and T, and what we do is an analytic continuation, and therefore you can see that this 4-point amplitude will have infinite number of poles at positive integer values of S and T, and this amplitude is also called Venezian amplitude, and this amplitude has a property that there are infinite number of poles, and these poles correspond to exchanges of massive higher spin particles. And because of the presence of this infinite number of poles, this has a property that this amplitude can be expressible as sum over poles either in the S channel diagram, S channel, or sum over poles in the T channel. Of course, the domain of convergences are different. The former one is for negative values of T, and the latter T channel expansion is for negative values of A. And this symbol is what is called a hook hammer, which is given as ratio of the gamma functions. And because of this property that it is expressible as sum over poles in one particular channel, these amplitudes are also called dual resonance models. And we'll talk about these in more detail later.
Just be clear, it's virtually not in this that failed. It didn't have an infinite power state. That's the state.
Sorry, could you repeat?
If you didn't have an infinite power of Australian master states and still tried to claim the amplitude be expanded in one channel,
It will fail.
yeah, and that's because of virtually not. So,
Yeah, exactly. The high energy behavior will be affected, and therefore, yeah. So the single channel expansions are very much tied to the fact that we have infinite out of massive Hasselbalch states. So one thing to note is that these single channel expansions are not manifestly crossing symmetric, although the amplitude is. So now to write down these single channel expansion or these series representations, what we use is the dispersion relations. And by dispersion relations, as we all know, that we can construct the full amplitude if we know the singularities of the absorptive part of the amplitude, provided certain assumptions about the high energy behavior and other properties are made. And so we start with a contour integration of this form, and then we deform the contour to infinity. And usually in quantum field theory, the contour at infinity does contribute, and therefore we require subtraction to write down dispersion relation to express the amplitude. But in case of string amplitudes, for example, this particular case, this amplitude has a high energy behavior s to the power t, and as we can see, if t is negative, then the arc at infinity can be dropped, and therefore the full amplitude is expressible in this way, the thing written in the magenta. And in fact, so for tree-level amplitudes, the singularities are simple poles, and from here we get the series expansion of this kind. Now, so the property of dual resonance model is that we can write the dispersion relation, this is also called fixed T dispersion relation, in this way by dropping the arc at infinity. So therefore, there are like expansion as sum over poles in one particular channel gives rise to the full amplitude. Now, phenomenologically, these dual resonance models were important in studying high energy behavior of hadron scattering involving pion scatterings. And so like back in 60s, those dual resonance models were very popular. But people noted there are some contentions. In fact, they were not adequate to describe the high energy pion scattering. Dolan, Horn, and Smith, they used finite energy sum rule to explain the experimental data of these pion scattering. But what they observed is that the single channel expansion, and at that time they were referred to as dual models as interference models, the single channel expansions were not adequate and required modifications, meaning there are additions of direct channel poles and then there are additions of transfer channel poles, but that gave rise to double counting, and one has to compensate for that. And so they proposed a model of this form, by which they could explain many of the experimental data. And in fact, the early founders of string theory were also a bit skeptical about this dual resonance model. For example, in the textbook, Green, Schwarz, and Wheaton, in like one introductory chapter, they mention they pose this question: is duality an approximation or principle? And they say the duality hypothesis never had more than slender experimental support, and the Veneziano model was merely an ad hoc way of satisfying this not so well motivated hypothesis. And in retrospect, if we look at the single channel expansions where we require to have the sum all the way up to infinity, is phenomenologically a bit disconcerting. That we have, it's also unrealistic from more experimental point of view. Like, do we really have to go to like infinite energy, or can there be a cutoff and still we can try to make some sense of effective string-like the theory? So our motivations are based on these premises. And in this work, the precise question that we pose is the following: can we obtain a field theoretic representation of tree-level string amplitudes such that the representations will satisfy the following properties. One, crossing symmetry is manifest, unlike the single channel expansion that we saw, where poles in one particular channel are contained. We would like to have a representation where poles in both S channel, T channels, and if possible U channels, they're all present. And the representation should be analytic and convergent except the location of the physical singularities for all kinematic values. And we can talk about regular terms. Regular terms, the way we are defining regular terms is the terms modulo or subtracting off the divergent pieces. We can call them contact terms, and the contact terms should also be finite. And that is necessary for writing down a Lagrangian prescription. And importantly, let us say we have a energy scale, which we call it R, and for certain range of kinematic variables, say S, and T. So SI, I'm referring to as S and T in general. The infinite series representation, if we truncate to retain reasonably finite number of terms n, which is either of order or below that energy cutoff R, then the truncated sum will exhibit important features of the actual representation. Or in a summary, what we are trying to say is that if we set a cutoff and we try to have an approximated representation, which will for a very high accuracy will mimic the original representation below that cutoff scale, and above the cutoff scale will violate or the representation will become invalid.
Why is taking the sum over poles in the S channel and the sum over poles in the T channel amplitudes averaging them? Not
If you average, yeah. So then if you find the residue, they will not have the correct residue over the pole. There will be a factor of half.
Yeah.
So that will not give you the correct residue. From the spectrum,
why do you want the correctness?
from the spectrum, you already know what is the residue. Like if you take gamma of minus S, gamma of minus E, whatever amplitude we have. Okay, so this one, you can find out what is the residue at S equal to something. And now if you average them half plus half, first of all, that is not also convergent, because half of that converges for S negative and half of that converges for E negative. Now, if you are just summing over half and half, and then you are trying to find out some representation at some value of S and T, let's say S negative, E positive, then one part will always diverge. So this is at the level of representation. So that series averaged over will not have a good convergence. And secondly, the residue that I am talking about. So you know what is the residue at, let's say, S equal to 2. And it can be directly computed from here. But from the series that you propose, like if you do half and half, it will have an additional factor of half.
Okay, and that's because you're taking the residue at a point which is outside the sum.
Yes, yes, in some, yes. So exactly. So that does not have good convergence problem.
So I also had something those flaws. In sense, so you are trying to take something that was a finite quantity, and you want to write down something which is going to have problems. So in the sense that you're trying to know three things, you have to normalize, etc.
Yes.
So I'm missing why you were trying. I mean,
When you say
you naturally think that a finite quantity is always better, right? Than having to sort of regulate and normalize and with all the problems that you have with it's so back into it. Yeah.
So if I understand your question correctly, so first of all, this quantity is very much finite.
Yes.
So there is nothing wrong in this. So only problem about this infinity is about divergence coming from the particular representations that we are using. So now we are trying to propose a new representation which will capture this finiteness of this amplitude.
Yeah, but if you are thinking about it in terms of a quantity,
Yes.
then aren't you naturally going away from this?
No. So yeah. I mean, we can still talk about
finiteness of this.
Yes.
Is to do with the fact that you have been able to do away with coincident point singularities, etc., etc. That is what string theory does from.
Yeah. So for this particular thing, only singularities are the integer values of SN.
Sure.
Okay. So now, if we can come up with a new representation,
Yeah.
which will be convergent for any values of SN. So that we can call as a field theoretic representation. And that will,
Are you thinking of an underlying field theory?
Yes.
With this?
right.
So if you start off with that and write down, I mean, it should essentially have problems of renormalization.
So exactly. So question is, if we go beyond tree level, like
Yes,
if we
yeah,
account for loops, so that much we have not gone. So our proposal still is at the level of some on-shell.
But
Like-
I think I'm just asking as a sort of overarching principle. Is it the overarching principle flawed? I mean, in the sense that if you're trying to replace a string theory by a quantum field theory, you're going away from the basic things that made the string theory nice, right? If you want to replace it by a quantum field theory, you're going to get all of those
that is
problematic aspects back, right?
that is, for example, if we look at the worldsheet integral, so we always have some kind of analytic continuation because worldsheet integral itself is divergent for case other than negative and P other than negative. So when we think about a theory, we always do a from the worldsheet to the target space time. We have in mind some kind of analytic continuation. So underlying string theory as a whole, I think they have a lot more problems, and when we do some analytic continuation, then we can still make sense of that theory, right? For example, this representation, I mean, if you are calling, if you are saying where the poles are, and those poles correspond to the physical spectrum, they're always away from the actual domain of definition of the string theory of the worldsheet string theory, right? So in a way, so I understand, I agree with you that like it's overarching thing, it requires a lot more corrections and a lot more things to do. But these are first step that we are taking.
Since you are talking about this, the fact that it doesn't converge, sometimes it's said that it has to do that you're using a Euclidean worldsheet for this formula, while real string theory should be Lorentzian.
Exactly. Yeah, that is one thing.
But with Lorentzian worldsheet, are there good convergent representations that have a good answer for the physical values of Mendelssohn, or?
Yeah, not that I know, but there are recent works by Sebastian Mizera and Lorenz Eberhardt where they mostly talk at the level of loop integrals, one loop or one genus, where they go from this Euclidean worldsheet to the Lorentzian worldsheet. And
these are nice.
Yeah, things are right. So it's again a way of regulating. So what I understand is like integration, they put some slightly imaginary part to the integration contour, this Z contour, and using that, still things can be made finite. So it's like how to put I epsilon prescription in defining the propagators. So that is immediately not visible. Okay, so regarding the cutoff that I was mentioning here, so this is similar in spirit to what someone from QCD community will see string amplitudes. So this is an excerpt taken from. So in 2024, after the strings, people were asked to write down what important questions they think to be considered for next few years, next in long term. And this is what David Koswa said. And I'll just read a few lines of this question. The string theory had its origin as a theory of hadrons. Utility of having a string-like theory of hadrons to bridge the gap between perturbative QCD and low energy expansion, such as chiral Lagrangians, would still be great. And if the required theory would be an effective string theory, by analogy with effective Lagrangians, it would still have a cutoff above which it loses its validity. So whatever I'm trying to say is a very approximate sense. And in stricter mathematical sense, things will be, we may have other bad things like divergence and so on. But still, in a particular energy scale or within a cutoff, we can try to connect both string theory and some phenomenological aspects. So this is the outline of my talk. I'll first talk about open string amplitude. Then I'll mention how we obtained the new kind of representations using symmetric dispersion relations. And then I'll mention how these representations or these dispersion relations can connect with asymmetry's bootstrap program. And I'll then mention about some closed string amplitude, some results, and finally ending. Before ending, if I get time, I'll talk about something how to go beyond 4 point, although that is still a work in progress. So now to understand what kind of representations are we talking about, let us first look at some examples and see if they also fit. So this is the integral representation, the first line, as we have seen. Now, using some change of variables, we can bring that integral to a new form like this, and then around z equal to 0 and z equal to 1, we can do a Taylor expansion and then integrate term by term. And integrating term by term, we will have a series of this form. Now, we may think that this is a perfectly valid series in the sense that this has now poles in both S channel and T channel. So this is a desired representation that we can talk about. However, the problem is this does not converge or has very poor convergence for this region. If we take the real part of S1 plus S2 greater than -1, so this has converges only for this part, and if we go beyond that, then the series again becomes very badly convergent. We have to include many terms to make it convergent. And therefore, this is not a desired representation that we can use. And also, like Giddings, using Wheaton's string field theory, he tried to write down a representation by dividing the worldsheet integration in two parts, one from 0 to half and half to 1. This is also a kind of regulating. And then we can, so he called each of them as S channel and T channel contributions. And then if we do a Taylor expansion around this point, z equal to 0 and z equal to 1, and then integrate term by term, then we'll encounter a series of this form. Now, this has some, first of all, the vertex has some kind of non-local terms, let's say, t to the power S1. So that is one thing. So, and eventually it should have, because, string theory is not local theory. So maybe non-localities are put in these vertices, but also this series is not, again, very convergent series.
Can I ask something?
Please.
So what do you call the first integral S1 channel and the second one S2 channel?
Yeah, because if we integrate, then we are going to get this.
Or the poles in S1?
Yeah, poles in S1, and that's why it's a very rough way of saying.
So can you clarify, like, what one more was asking, like, can you expand in both channels? You said that there is no overlapping region.
Right. So this is an expansion in both the channels. By expansion in both the channels, I mean, okay, right. Overlapping region will be real part of S1 negative, real part of S2 negative.
So
Then, yeah, but then you would miss out the poles, physical kinematics, because poles are in the positive integer values. So now, as soon as you try to do analytic continuation, then the series becomes, then these representations become very very badly convergent. That is a problem. So yeah, so this also suffers from the same problem. So now, using crossing symmetric dispersion relation, we could come up with a series of this form, and numerically, and also afterward, we have done analytical proofs to show that this is a very well convergent. This even converges for any values of S1, S2. Note the presence of a free parameter lambda, which can in general be complex. And after we sum over all the modes, like n from 0 to infinity, then the lambda dependence actually drops out. And what we have on the left-hand side is lambda independent. So this is the representation that we are talking about. And for the rest of the talk, I'll state some aspects of this representation.
Is it fair to say that we would expect that in string field theory, in some charts gauge or whatever, for the definition, that it must be true that this happens and you should be able to write it from string field?
Yeah, it's a good expectation. And so I'm not an expert in string field theory, but talking to various people, what I have learned is that there is a possible way to connect it to string field theory, because the way these moduli space integrations are done is some way capturing the pole terms and the contact term in different regions of the moduli space. So indeed, it has a flavor of the string field theory in calculation.
But it's not have to do with probabilities.
Yeah, so far, like I don't know of any concrete calculation that has been done to match the. Yeah.
So how can those limits be different if then the sum is in there?
Yeah, so no, so this is the a particular summand I'm taking a term. This is not the full thing that you reduce. So,
That's it.
yeah. So what I was planning to say is that so now if you take lambda to infinity, the summand actually looks like this, and this is exactly what we obtained earlier. So there are ways to take various limits of lambda, and then the this representation will get back to the earlier representations that we know about. For example, if we take lambda to infinity, then we get back the thing that we obtained earlier using this change of variables.
What
And
about the convergence property? It depends on lambda.
yeah, so I'll come to that. First of all, if we take infinite sum, then yeah, so it is independent of lambda. So now, by convergence, what we usually mean is that if we take 10 terms, how much does it converge to the actual value? And the short answer is that lambda has to be less than that 10. And in that way, so when you say effective picture or something, so lambda kind of regulates an energy cutoff scale. And it should be below the number of terms we are keeping in the truncation for good convergence.
So when you say that you take this lambda group to infinity, then you get back the previous expression.
If we take lambda infinity, then the point is we have to keep infinite terms. And that is why the convergence is broken. And that it should be, because this is not very well convergent. So we have to take many terms.
So if you take the limit, you still
Yeah, we
Yeah,
still
it does.
exactly. So limits are just to illustrate that we get back, but I'll not talk much about the limits. Limits are not very significant.
So why is this field theory?
Yeah, I'll come. Yeah. So yeah, I mean, it's true intrusions is not a field theory, but I'll say why we are calling it an approximate field theory. Yeah, exactly. And so lambda going to minus S2, this is the usual fixed T expansion that we encounter.
Is it something like fixing a gauge?
One can think of that. Yeah, some gauge or field redefinition ambiguity.
I'm saying this because it's very nicely.
Yes,
If I can, you're looking at an amplitude.
Right.
But if you can track back to the action,
exactly.
whether you use
It
the
will-
square root
exactly.
or other one.
Or we do
constraint system.
Exactly.
Kind of a thing.
right. So lambda can be thought of as some parameter
Auxiliary-
coming from auxiliary variables or
Multiply with equal
right,
to something.
exactly. Or doing some field redefinition ambiguity. Yeah. So crossing semi dispersion relations were studied earlier back in 70s, again mostly in the context of ion scattering by many people, Robertson, Khoury, Mahuroy, Wonders, and we have borrowed many of their results, but eventually we have also come up with some new kind of non-trivial crossing symmetric dispersion relations.
That's right.
Yes.
You just said, so why is it greater than the other two? You'll be crossing symmetry managed.
Crossing symmetry is manifest and convergence is also manifest. So this is a table to show the convergence property. So here we have truncated the sum. We have fixed lambda to 8.5 some value, and we have kept 25 terms. And for these choices, so these are very random choices. Our representation matches very well with whatever is expected. And as we can see, the other two, like if one converges, the other one does not. So, like between the other two, like one converges in some domain, but the other does not. So that is the advantage of using the new representation.
But just to understand the inclusion bit better, I mean, is it also true that you think that if we can make it convergent in a larger region, then in a S-matrix bootstrap, we can put those constraints so we
Yes.
can find more state.
Exactly. So the question is right, precisely. The question is like what is the analyticity domain of the dispersion relation that we are using, and that's an open problem. But this definitely has much bigger analytic domain than the fixed T dispersion relations. If we use this Roy's equation, the compact type of part, then this the Lehman-Marta ellipse, those things, they definitely get bigger.
It's going very one comment that is if lambda is more than 25 that absolutely high.
Exactly. Then convergence becomes poor. Right? Lambda has to be of order 25, less than 25, better.
And given this it is not going too badly, so.
Yeah, in some region it is not going too badly. For example, in this region, you see, then it's 10 to the power minus 3.
Yeah, I mean, of course, and this one is going on better.
Right. It's not very bad, definitely.
So this will read from the previous from the what just for the background, like what was the case or somehow lambda appeared.
Right.
And what is the origin of that?
Yeah, origin of lambda.
See.
So we have a crossing symmetric dispersion relation, and then we are playing with like chronologically. So we first started off with the local crossing symmetric dispersion relation, as I mentioned, and then did some change of variables of the S1, S2, these parameters, and then we saw that because of the change of variables, our amplitude, since it remains fixed, we can introduce auxiliary parameter lambda. That was an observation, but that has some important consequence, as I mentioned, because now we have a new kind of dispersion relation to begin with altogether, which has that lambda parameter inbuilt, and that will kind of connect to known dispersion relations. So right now, to answer in short, we have a wave of unified dispersion relations. I'll talk about it. Okay, so this is more physical amplitude from the practical point of view, because this describes open string amplitude. This appears in superstring. And this is also used in studying fold gluon scattering. So for that, we have to multiply it by this tensor structure, trace F4. Or if we want other scattering, we have to have the appropriate super partner of this trace F4. That will describe actually this describes the mass, the lowest massless states in the spectrum of open superstring theory. And yeah, so as I mentioned earlier, that this series has a larger domain of convergence for S1, S2. So this bookhammer will actually take the form of a polynomial of order n-1. And so lambda can be attributed to field redefinition ambiguities, meaning if we have an underlying Lagrangian, we can do field redefinition, but still the amplitude should remain invariant, unchanged. And lambda can be complex number, but for convergence, we'll require real part of lambda to be greater than -1. And an asymptotic analysis reveals that for large value of n, the summand goes as n to the power -2 minus lambda. So therefore, having large value of lambda improves the convergence of the series. But again, lambda cannot be too large if we are truncating. So it has to be adjusted appropriately. And so the poles are at positive integer values of S1, S2, and one can check that on the poles, the residues are actually independent of lambda. So therefore, the physical content, the spectrum, they are all independent of lambda. And in that way, the lambda dependence can be pushed to the contact term or the regular terms. And by regular terms, what we mean is that, so now we have a representation from where we can interpret each n level as terms coming from a particular mass level, and then we can subtract off the pole terms, and what we are left is the contact terms at every mass level. Those will have the lambda dependence, and interestingly, if we sum over those contact terms, they will become finite. And in fact, in this representation, each summation over each terms will be finite. And that is very much like the string field theory, because in string field theory also the sum over S channels T, like roughly I'm saying S channels, T channels, and the contact term, they're individually finite. So like here are a few examples of first three mass levels. So this one is the massless pole, which is coming from setting n equal to 0. And this one is these are the first, second, and third massive poles. So things in the curly bracket, they are the residues by poles, and they contain information about what spins are being exchanged. For example, if we do so, this is written in terms of Gegenbauer polynomials because we are dealing with scalar amplitudes, and in any high dimension, they can decompose in terms of Gegenbauer polynomials. And so this is the exchange of a scalar. This is an exchange of a spin 1. And at mass level 3, we have exchanges of a spin 0 and a spin 2. This will correspond to a spin 2 exchange. And these are the contact terms, which are regular terms, do not have any poles. And they are lambda dependent terms. X and Y are these combinations of S1, S2. And so one trivial thing to note is that for unitarity of the amplitude, we require the partial wave coefficient. So these are the partial wave coefficients. From here, we can read off. The partial wave coefficients have to be positive, and because of appearance of this factor 10 minus d, this sets the upper critical dimension of superstring theory. Because beyond d equal to 10, this will become. So this is one way of one consequence of this decomposition, or one consequence of having the greater than 10. The amplitude will start becoming non-unitary.
So, yeah, I mean, you started with the Venetian one, right?
Now we move to superstring amplitude.
Oh,
So this one is, so when the difference with Venezuela is there is no one.
yeah, I know.
Okay. So if we do the same thing in Venezuela, we get 26.
Can you comment on the contact terms? So presumably they will have higher and higher derivatives as we go up.
Yeah.
How
So
does the-
So you see this x square, xy, and x are these functions. So in that way, they are having these high derivatives.
Yeah, but they increase with the mass level. The degree of the.
Right. Yeah, they increase with the mass level. Yeah. And then what we can do is for particular values of S1, S2, we can sum over them, and they will still become finite convergent.
Sorry, just
So these are just terms. These are terms.
For n equals to 0, you get p 0.
Exactly. Yeah. So these are just command. Yeah, the massless pole is independent of lambda. Sorry.
Unitary, if you write down the actual amplitude in terms of the Gegenbauers and read off the partial waves, once you get the
Same things. Yeah. Just to illustrate, you get the same. I mean, this thing you could even do with fixed T. Yeah, nothing special about it. But special here is this contact terms. Is getting these contact terms. This is something that one would not be able to do in fixed T.
And lambda equals to 0%.
No. Okay. Lambda equal to minus S2. I'll come to that.
But what will it correspond to if I put lambda equals to 0?
It will nothing. So lambda equal to 0 is still finite.
But it should be something represented.
This is one of the representatives. So the range of lambda, real part of lambda should be greater than -1. So lambda equal to 0 is just a kind of ordinary point.
But this field theory interpretation like this is a bit ambiguous, right?
Bit ambiguous. Field theory interpretation will be ambiguous because of the presence of contact terms. Contact terms can be moved. So okay, so this is what contact terms can be moved in difference. So this is just a very toy example of, let's say we start with a Lagrangian with massless fields phi. There are two massless fields, let's say, and some massive fields. And if we write, then there are, let's say, n massive fields, they have cubic interactions. And if we write down the Lagrangian and for simplicity, we are assuming some kind of color ordering so that we are talking about only partial amplitudes. The full amplitude will have this form. Now, if we do a field redefinition of something like that, so then the contact terms will change. Now, let's say effectively, we are looking at some energy scale such that some massive exchanges we can ignore, meaning we can put them in the contact term. It's just a kind of EFT way of expanding. Then we see that the amplitude will start depending on lambda because of that particular expansion, because of that truncation. And once we include all the things, then the amplitude will still become any field redefinition independent. But if we truncate what we do in a EFT, then that field redefinition ambiguity will start appearing. And so this is one way of interpreting that field redefinition. And here also you see that if we truncate, then it starts depending on lambda. And if we add more and more terms, then the lambda dependence goes away. So then we come back to the question that if we indeed have to sum over find infinite number of terms, then in what sense we are calling it a quantum field theory representation? So in our representation, what is happening is that truncated sum has this lambda ambiguity, but this ambiguity goes away as more and more terms are written in the sum. Now, so here is a plot of amplitude with respect to some energy scale, the center of mass energy, let's say, is with truncated sums, meaning where the truncation is set to various values. Let's say we keep first 15 terms. Now, for the truncated sum, if we look at the amplitude for center of mass energy less than this 15, then this is a very good match. So this black curve here represents the actual amplitude, actual value that we are getting. So up to S less than that truncation, it is a very good match indeed. Like up to some 5 or 10 decimal places, it matches very well. And after that, it starts breaking down. And similarly, if we set the truncation to n equal to 20, then below 20 unit of energy scale of center of mass energy, it's a very good approximation. It mimics like it gets almost the actual value.
This one. So you're matching against that field theory that you wrote down?
So yeah, so these colors are the field theory, and this one is the actual amplitude.
And you're getting a match. But in the actual amplitude, you still have a mass-based field theory.
Right. Oh, you're saying that why this is a continuous thing. So we have slightly shifted by 0.1 I epsilon. We are taking a model. So we are slightly off the real axis for plotting purpose only. Just a numerical thing. Otherwise, yeah, we'll hit the points. Definitely. Yeah, thanks for this question. Yeah, so and S2 we have set it to some value like that, some physical value. And so this is the way we have plotted, and we have actually plotted model, so therefore you don't see the like oscillations. Something goes below 0, negative, and then positive.
So the truncation that you are doing, so does it correspond to truncating a degree in lambda, the polynomial in lambda?
Yeah, so definitely, because if we do the truncation, so from this representation, let's say n equal to 25. So since this is a polynomial, so we won't have anything beyond lambda to the power 25. So yeah, definitely that's a way of interpreting. So the point is that within that truncated value, if we plot m as a function of lambda, let's say here we have kept truncation parameter to 20, and then we are plotting m with respect to lambda, then we get almost a flat line. It's almost a plateau with slope like almost equal to 0. So this is the approximated thing that we are calling a field theory representation. An approximated field theory representation where the amplitude is such as if it is not even changing with any lambda. So del m del lambda is almost 0. So this is the way we are trying to interpret as a approximate field theory.
Sorry.
Yes.
Right.
Right.
Last one. Yeah, I guess we'll say
So up to this, I think if you are convinced that if I plot, if we look at the value from the truncated sum below that cutoff scale. So here we are setting the cutoff scale, let's say n equal to 15, and if we are looking at the value below 15, then the answer that we are getting is very much close to the actual value. So now we can ask, so this is plotted for a particular value of lambda. How the amplitude is changing with lambda within that truncated series. That's what is plotted here. So
sorry, but that value of lambda you're saying is very specific to that number. If you change the lambda, you go to a different scale.
Exactly. So exactly, it's like a cutoff scale. We are changing lambda. We are going to a different, not different theory, but going to a different energy scale.
But so in this thing is so you cannot like so this imagination is very crucial, right? Because
otherwise there will be divergences, but it is not that crucial also.
No, let's say I'm interested about the poles, like what are the excitations?
Right.
So then that does not match.
No, so as I told, so let's look at the representation here. The residues are independent of lambda. That is because, let's say if you put S1 equal to N.
And that is not going to match the field theory answer, right?
Because there it was independent of lambda. So field theory, I mean approximate field theory that we are saying that we put a truncation instead of going all the way up to infinity, we set up to let's say 20.
But that is like a stringy tower up to that level, right?
Yes.
Up to that level.
Up to yeah, and anything within that level.
So and that also has a, let's say, something like a massless spin to particle in that spectrum.
So okay.
The
So,
graviton is there. That's
so here the graviton is not there because this
Why?
is open. So this representation, if we do okay.
Oh, this is open screen.
This is open space. Okay. Just right. Because graviton started appearing when we talk about loops. If we consider
Okay.
gluon scattering but involve loops, then only graviton will start appearing.
But
And
yeah, and I'm not disagreeing is what you will do, but if you did this for the closed strings. Then what we say is going to keep you in the face right, because it
We
will
have
always
always
have,
yeah.
right, it
Will
will
also-
always have a spindle part level.
Yes, it will have. But
So it's not a-
I'll come to the closed string. and
It's
then-
not a field theory in that sense, it's not a. field theory of-
So there also we can get away with that. Yeah.
Probably, if we treat the
Graviton as a field, the time as a field.
Yeah.
Automatic.
In a perturbative, because we have a representation of Virasoro Shapiro amplitude as well, and then we can come back.
Yeah, then I'll ask you
Yeah,
what
sure.
happened to and what happened to divergences, right? Because
Exactly. Yeah.
because that's
So
not-
those
not
are-
normalizable, right?
So
Yeah.
again, when you say renormalizability or those issues,
Yeah,
that they'll come like when you take into account loop effects and everything.
Yeah, it'll hit you in the face. Right?
Exactly, it's true,
So
true,
there's
true.
no way
Yeah.
that
So
that can,
yeah, I mean, I agree that maybe this cannot be applied to incorporating loops. So maybe it stops here, this representation. So that answer I don't know. But at least at the level of tree level, we can get.
Sorry, that's possible. The fact that this derivative in lambda is 0, you could also invert the logic and use it as some type of constraint. So
Exactly.
how do you-
That's what we do for S matrix. So I'll come to that. Precisely. Yeah.
And you will explain the last graph, sorry.
Exactly like it. So last graph, so let me explain the how it is plotted. We take the truncation up to 20. So small n equal to 0 to capital N equal to 20. And then we put the value of S1, S2. Again, this is mod M to be very precise. No, sorry, this is actually M. Okay. And then we are seeing the evolution of M with respect to lambda. So we are changing, so this is the lambda on the x-axis. We are changing lambda from this value to this. And what we see is a very flat curve. And that means that del m del lambda is almost near equal to 0. In fact, if we compute the slope, it will be in 6 or 7 decimal places or even. So in continuum. So in that way, within that cutoff scale, we are having a representation which very much closely matches with the actual one.
But you cannot go beyond lambda equals to 20.
So and that is not expected. So it is like phenomenological, we are looking at an energy scale. And if we have to observe, we better keep the experiment set up within that energy scale.
And in a sense, that is why you're trying to call it a field theory.
Exactly, yeah. In a
So you're sort of have a scale.
scale, exactly. Like cut off
kind
scale,
of at that.
yeah. Field theory will so this is very much like the beta function how we. So, okay, let me now explain some ingredients that have gone into deriving this. So, the series representation that we obtained uses process symmetric dispersion relations. They were studied back in 1970s by Oberson and Puri. And then in recent years, Anindya and his group has studied this thing and extended in various possible directions. And then Choming-Song also made an important contribution about how to find a local dispersion relation. So the way we go is as follows. Let's say we have these 3 variables S, T, Q. 2 of them are independent because of certain thing. So this mu is like 4m squared. And then we relabel the variables in S1, S2, S3 by doing a shift like that. And to present the derivation in the simplest form, we have ignored the S3 channel cut such that we are dealing with only 2 channel symmetric amplitudes. And so, therefore, we will fix S3 and look at singularities in S1 and S2. and the singularity is, so will be there for the positive values of S1, S2. Okay. And then what we do is we actually map this S1, S2 to the complex plane via this map. So this Z is a complex plane, variable of the complex plane, and we map S1, S2 by this. And here A is a constant, and A can be worked out. Like if we know S1, S2 like this, and A is a worked out. And basically this gives an equation of a hypersurface, a conic equation. And on that hypersurface, we are studying the analytic properties of the amplitude. So basically, we are bringing the singularities of the amplitude to that complex plane. So the poles, so basically we can now revert this map. We can ask what is Z in terms of S1 or S2. And here Z is inverted in terms of S1 and A. And so the poles will be in S1 channel will be from A to infinity on the real axis in the S channel. They will be mapped to the upper half unit circle in the complex plane, and similarly S2 will be mapped on the lower half unit circle. And then importantly, so we need to also specify the high energy behavior, and we can see from this map when Z goes to e to the power I pi k, so k is 1 and 2. When Z goes to e to the power I pi k, S1 goes to infinity and Sj, the other variable, that remains fixed. And that is exactly the Rayleigh point. So in the Rayleigh limit, what we do is take S to infinity, keeping T fixed. So the Rayleigh growth is specified at those endpoints. And there we specify the high energy behavior of the amplitude like this. Let's say, so this M tilde represents the amplitude written in the Z and A variables. And at Z goes to e to the power I pi k, this is the way amplitude should behave, order of this. And so this specifies that M is growing at most at order S1 in the S channel. And then we also need to specify some other properties like real analyticity. So that is basically the poles or the singularities are located on the real S plane, on the real S axis or T axis. And also because of the crossing symmetry function, M tilde will be function of Z square. That can be checked. Now, utilizing this property, we evaluate this integration. And when we evaluate this integration, this is a contour integral. When you evaluate that, the poles or the singularities are located on the unit circle. So the discontinuity of this amplitude will be slightly above and inside the real circle. So from there, the discontinuities are going to come. And if we do all these things, so we get a dispersion relation in the Z and A plane like this.
So real analyticity is where we get this from.
Yeah, definitely. So real analyticity in this case is basically the imaginary part is given by f of z minus f of z star. So, like f of x plus I epsilon minus f of x minus I epsilon. That
is really.
yeah, that is a discontinuity. Simplest thing.
And locally, or you are using.
Okay, locality directly we are not using, but they will come as a consequence. So okay, locality. I'll just comment on that, how the locality is. Okay. So from here, if we now go back to the S and T plane, we get a dispersion relation of this one. And here we see what is happening is that this one, A of S1, is the absorptive part or the cut in the S channel of the amplitude. So the first argument is sigma, and the second argument has changed to this, where A was again this value, combination of S1 and S2. And then what the point is, because of the appearance of S1 plus S2, whenever S1 plus S2, that combination goes to 0, this representation will have spurious unwanted singularities. And that actually made the convergence domain of convergence narrower. So therefore, this suffers from those spurious poles or spurious singularity problems. And one way to get rid of that spurious singularity is do a kind of Taylor expansion. And if you do a Taylor expansion, and so this kernel can be written in a slide algebraically in this form. And so then the point is do a Taylor expansion around A equal to 0. And whenever we encounter negative powers of this S1, S2, we just throw them by hand. And if we throw them by hand, we get rid of all the spurious singularities. And finally, so effectively, this is like changing A to this value, sigma y by sigma square plus y. This is some details. Sorry for that, like going in too much details of this technical things. But finally, if we throw away all the non-local, so those will be kind of non-local terms. Like now, when we throw away those spurious singularities, whatever singularities of the amplitude has will be retained here. No additional singularities at the level of the dispersion relations. And effectively, this is what we are gaining. That the second argument has changed from this to this. This is y by sigma and has no other singularities. And what it means is that if we do a Taylor expansion or Wilsonian expansion, we only retain positive powers of x, like positive powers of S1, S2, and S1 plus S2, that combination. So this is what we had obtained earlier. And then we can do a further change of variables and introduce the free parameter lambda. And the advantage is that now note that this one needs us to evaluate amplitude at 0, 0. And if there is a massless pole, then this will be problematic. But now we have to evaluate the amplitude after inserting or including this lambda variable. We have to evaluate at a different point. And we can get rid of that. So we don't need to evaluate at s equal to 0, t equal to 0. So, and that's why it is better in and more advantageous. And in fact, it has, again, a larger domain of convergence. And another important property is that now, if we look at this thing, it has a few parts. Like, so this is the amplitude rewritten here. Now, if we are dealing with some amplitude whose arc at infinity is decaying, that is high energy behavior is, it has a softer high energy behavior, then these two things will cancel because of Cauchy's residue theorem. What we are left with is this one. Then if we tune lambda, let's say lambda to minus S2, we see that this one reduces to S2, because if we set lambda equal to minus S2, this one actually cancels, and then this becomes minus lambda, which is S2. And the kernel here, actually there's a cancellation and reduces to this. And this is nothing but the fixed key dispersion relation that we are familiar with. And in that way, the dispersion relation that we have obtained is kind of like in different limits, gives us back the known dispersion relation. And that's why we are saying that it's a web of unified dispersion relation that we have using this lambda.
So even complex game where you had that J equals to with our alpha.
Yes.
That game.
Yes.
What does it mean to have lambda in this picture?
So that I mean, okay, there is a kind of interpretation where in that picture, what we can do is we can so wherever we have defined this S1, S2, we can shift by lambda here, but that is not a very useful thing. So to answer is instead of SK, we can think of SK minus lambda or plus lambda.
But that has to satisfy the constant that S plus T plus, you know, whether you return.
So exactly. So right. That goes back exactly. So that constraint is not readily required if we are really with local like two-channel symmetric, but that constraint will be important if you're dealing with full crossing symmetric, because there the T channel has to be explicit. So here we have still the freedom of changing S1, S2 arbitrarily without caring about S3. So this is what we have gotten, like a web of this dispersion relations.
So in the lambda dispersion relation, the information about high energy behavior was never there.
No, it was there. Yeah, it was there. So that's what I have done. So let's say we are looking at an amplitude whose high energy behavior is like this. It can at most, actually, okay, it's a typo. It should be less than 1 by S. If it goes as less than 1 by S, so then we start off with a contour integration of this form. Okay, and then if we take sigma, it actually decays. And therefore, we can forget about the arc at infinity. And then we impose the condition that constraint that because of crossing symmetry, evaluation along the S channel cut and T channel cut, they should give the same contribution. That is just an input, and that will give us a constraint in the form of some differential equation, solution of which will become this. So S2 prime of sigma has a specific solution of this form. And so this has some particular feature. If we set sigma to minus lambda, S2 prime goes to infinity. And if sigma is infinity, S2 prime goes to minus lambda. So now, talking about the high energy behavior, or if we consider an amplitude which is growing, instead of this order one, it can go to some S, some power of S, let's say. What we need is we need to tame the behavior at infinity, meaning add some counter terms at infinity. And because of the very specific property of this solution, we can put the counter term at infinity by doing a low energy expansion around S1 equal to minus lambda, S2 equal to minus lambda. What it means is that now instead of considering this contour integration, we have to add few more terms, doing a Taylor expansion around S1 equal to minus lambda, S2 equal to minus lambda. Then we can get rid of the arc at infinity. What will be left with is some unconstrained constants that we have to specify. So that is like specifying more low energy data or Wilson coefficients. So that is how we add subtractions, and that can also be done here. And curiously enough, so this from this sigma is a so S2 prime is a monotonical decreasing function with sigma. So at sigma equal to infinity, it is minus lambda, and then as we noted, so from infinity to it is going to minus lambda. Therefore, if we then substitute this to here, so and let's say we're considering an amplitude which has the Rayleigh behavior, like S to the power some polynomial in T. For a specific example, let's say S to the power 2 plus T2. If we plug that in here, what we get? Sigma to the power this minus 2. And when sigma is taken to infinity, this is nothing but sigma to the power minus lambda. So therefore, if we choose lambda appropriately, a large value of lambda, we do not even need a subtraction. So this will also work for amplitude, which instead of having the high energy here as order 1, if it closes S to the power 2 something, then also, or S to the power 2 plus T something, then also it will work. And that is the reason it works for positive values of S2 as well. Like we do not have to restrict T negative in the case of usual fixed T dispersion relation. And that is the advantage. So that's why it is so well convergent. So as I mentioned that this can deal with massless poles like this form. And also, I mean, so far I have been only talking about tree level amplitudes, but at the loop level is a very specific example which appears in the n equal to 4 super young, massive n equal to 4 super young study, centiliter amplitude. And that can also be expressed using the our dispersion relation that we can take. Okay. So now the question is, so the single channel expansions or dual resonance models that we have been talking about. Now, question is, are the string amplitudes only unique solutions or only unique examples of those dual resonance models? And to answer this question, we resort to bootstrap philosophy and put enough constraints and try to see if we are getting the string amplitudes uniquely or not, or are we getting some other amplitudes as well. So what we do is like use our dispersion relation to study this bootstrap. So first, this is a partial wave expansion in terms of the Gegenbauer polynomial in high dimension, and then we can find out the absorptive part, and we'll plug that in the dispersion relation. So the CLNs are the absorptive part of the partial waves, and the usual constraints are there, like unit implies the CLNs to be positive. And also, we make some assumption about the spectrum, that is exchanges, and the polynomial should be bounded from above. And also, so to write down this, because we want to, like, we also require the data at S1 equal to 0, S2 equal to 0, we have subtracted out the massless pole. And that is possible because we are dealing with tree level. If we go to loop level, that will not be, like, it requires more careful analysis. But for the time being, we have just subtracted out massless pole and we'll plug that back in. So then, if we use this representation or use this expansion and plug that back in the dispersion relation, this is a generic form of one parameter ambiguity amplitudes that we obtain. So here we have the lambda. The CLNs are the unknown things. Spectrum is specified because it has poles in positive values of S1 and S2, like that. Now, this representation actually holds in two cases. One, where we only have scalar exchanges, and there can be finite or infinite number of scalar exchanges, no restriction. Because what happens is that this exactly cancels, because for the scalar exchange, only term that contributes is L equal to 0. So this and this will cancel each other. But as soon as we turn on any spin exchanges, then we cannot, like, the truncation is not possible without lambda being explicitly there. So for infinite, I mean, if one spin exchange is allowed, then we have to allow for the full tower for the lambda dependence to go away. And we can check that this representation is actually valid for open string amplitude or Venezian amplitudes and other hypergeometric deformations that have been talked about recently in the literature. And the objective of Bootstrap is to find out this CLNs that will give the spectrum of physical information subjected to some constraints. So one constraint that we can impose is del m del lambda equal to 0, or since we are doing numerically, we have to set a tolerance, we have to set a cutoff, and within that cutoff, we have to assume del m del lambda equal to 0. In fact, we can do a bit more. Instead of del m del lambda equal to 0, we can also specify higher derivatives to be also 0, because finally it is independent of lambda. So these will give one a set of constraints, and on the top of that, we have some additional constraints which come from looking at the string amplitude. So in the string amplitude, what happens is that if we set lambda equal to 0, let's say, then we can write down an expansion. So this is the amplitude minus the massless thing, and this is the Wilson coefficient. This exactly cancels, which is minus pi square by 6. This exactly cancels the other part. So W00, we borrow that philosophy from there, that W00 should be equal to this one. And this one can be evaluated if we look at this amplitude. So we can compute W00. So another constraint which comes from looking at the string amplitude, the motive, that's the motivation of choosing this as a constraint. So we fit that in also. We put this as a constraint, and also, so actually what is happening is that this is nothing but the amplitude written in the forward limit, setting t equal to 0. So in a way, we have an amplitude which is single channel expanded only at t equal to 0. So this constraint says that. And then the idea is to do some linear programming where we have to we actually maximize this thing, W00. Now that is a very ad hoc way of doing. Why should we maximize? But I'll try to explain. I'll give some motivation behind that. And so then we can plot the solution in the space of Wilson coefficients by fixing W01 and W10. So we can make a plot. And these are the old constraints that we already have, del m del lambda equal to 0. And this is what we get.
Is there a natural point of taking the derivative of lambda? Any natural point of lambda or take derivatives?
So I mean, it cannot be one single point, because otherwise then then we are specifying del m del lambda equal to 0 only at point. But what we require to be the data to be specified is over a span of values of lambda. Then only we get the solutions. Because if it is one point, then it is of no use. We want.
How do you numerically implement the optimization parameter?
Yeah, optimization parameter. So we do SDPG. And also later we try to do using some machine learning as well. Like we define some loss function using these things and then minimize it. But this plot is done based on SDPG. So this is the solution of basically the CLNs or the amplitude in the space of W10 and W01. Here is a string point, and this hit plot or this color code is to show that more bluer it is, more it is satisfying duality, meaning like more it is satisfying this constraint actually. So and by duality, what do we mean is that we can have a single chain expansion of the amplitude, and we can plot the actual amplitude on the top of it. So let's take the string point here, and let's plot the curve for S2 equal to very near to 0 and away from 0. And we see that the string is always on the top of its dual amplitude. But for a random amplitude, like somewhere here, if we plot M, then near S2 equal to 0, it is on the top of its dual. But as soon as it goes away from S2 equal to 0, let's say for this value, it deviates. So this is the deviation. So what is actually happening is that all other amplitudes are actually scalar deformation of the string amplitude. If we take away one scalar mode, then we are violating the high energy behavior. And therefore, like when S2 is negative, it will go to a constant instead of following S2R. However, all the amplitudes on the black curve, a string is a part of which, on the black curve, they satisfy exact duality. Meaning they are always given in terms of signature extension.
Sorry, in your plot, what was the point D?
D was actually a random point here.
I mean,
It's not any specific
oh,
thing.
it's not
It just
any
yeah,
known-
it's not specific. I mean, okay, I have just copy pasted. So yeah, so string is here. So important points are this one and this one because this is just 1 by S1 S2.
But those theories still away from the boundary. They are inside the allowed region.
They are inside the allowed region. Exactly.
What is the line?
What is the line? Exactly. The question is what is the line? Yeah. So this black line actually satisfies this constraint. And this is a constraint that will be satisfied if the amplitude has duality, meaning dual expansion for all values of lambda or all values of S2, S1 and S2. And there's an analytic solution for the black line, which is given this. This is hypergeometric deformation of the string amplitude. And we get string amplitude if we set R equal to 0. If we set R equal to 0, then this is nothing but gamma of minus S1, gamma of minus S2 divided by gamma of 1 minus S1 minus S2. So the black line, first we found this and then in paper by Mansfield and Spradlin, they found this analytic solution of this. So that's the black line. And in fact, the black line has all the features of, at least at 3 level, 4 point, all the high energy features of the string amplitude. And they have the same spectrum. So this black curve is actually varying with respect to the parameter R. R is -1. So -1 is all the way here, where W10 and W01 will be infinity or minus infinity and plus infinity respectively. And R equal to infinity is this point, and this is nothing but 1 by S1 S2. And string is like here.
So what is the high geometric information?
So yeah, physically I don't know, but it is a representation which has the at the level of tree level, it has the same spectrum content, meaning same residues over poles. So yeah, so that story like if we string theory is supposed to have an underlying CFT.
Spectrum change, right?
So from the CFT, yeah, so now it can happen that at tree level they are still same, but at loop level they will change. So maybe I don't know the answer whether they can not, but it is possible.
Is it possible that there are so many string theory?
Yeah, so that's the motivation. So we don't know. At least at the level of 4.3 level, we are unable to rule out any theory with this specific set of constraints. So we need more analysis, definitely. So and that is the motivation behind all this work.
So we have roughly 16%.
16. Okay, I can stop at some natural point. You just tell me when to stop. So otherwise, I have some 10 more slides to go. So
Right.
yeah,
You have time.
yeah. If I need to stop anyway, you just tell me. Like give me 5 minutes and then I stop. Wrap out. So anyway, these are the numerical things of the CLN. So like these are the exact things that we can have, and then like our numerical things also match quite closely. So the question was, we made an assumption about W00 of extremizing W00, but that is actually related to some quantity which is given by this linear entropic quantity. And here we are computing linear entropy or entanglement in the space of the helicities of the amplitude. So if we are throwing gluons, and we can then compute entropy, or change of entropy between its final states and initial states.
Sorry, I missed something. So why are we minimizing?
Yeah, so basically during the bootstrap thing, I made a comment that we were It's called linear programming.
Yeah, you want to.
Yeah, can it be related to some physical quantity? Exactly. And that justification comes from here, looking at some quantity called linear entropy. And W00 is actually proportional to that. So if you are doing gluon scattering, then that is related to that. And we want the so the feature is that minimization of entropy gives rise to the maximization of W00. It's not very well founded thing, but it is just a connection.
Wilson coefficients are equivalent to.
Yeah, proportional. Exactly. W0. Yeah. Yeah. So right. So that's how it is in the forward step.
Yeah, so. Is it entangled entropy or-
It's linear entropy. It is linear entropy. So we define a mixed state like this. I mean omega like this, and then we can compute its density matrix. And this is what linear entropy. So it's okay. It can be obtained by setting n equal to in the Renai entropy.
So,
In the Renai entropy,
n equal to what?
n equal to 2.
Second.
Yeah.
So I'm very confused also. Wilson coefficients are to do with the
Low
value
energy.
of states.
Yeah. Right.
So
because-
what is the entanglement between? Is it between?
In the helicity space between the incoming and outgoing states.
No, I'm saying if I have a theory,
Hmm.
if I run it down, I get these W's that you set, right?
Right.
What does this have to do with the entanglement?
So this is a particular case where we're talking in the scattering process. So I don't know about the full theory, but let's say in the scattering process, we are looking at the how the final state helicities are connected to the initial state helicity. So when you are throwing the for gluon scattering, 2 to 2 scattering, the initial things can have different helicities, plus minus plus plus.
They would have some entanglement. I
Yeah.
buy that.
So now in the
Why is that equivalent to Wilson group?
No. So this is an observation. I don't know why. This is an observation that we are making that in the so if we compute this change in entropy, linear entropy, then this is actually proportional to this W00.
No, but that's for just one case. Is that an accident? Is that something that you?
So
If you're going to sort of, sell this as the reason why you have to sort of maximize it.
okay, we haven't gone that far.
No, but then the point is it just this particular amplitude that you're saying?
No, so we have okay. We also have this graviton amplitude. They are also the same thing works.
So are you saying this for string theory? Are you saying this for quantum field theory? What are you saying this?
Right. At least for maximally supersymmetric theories, we are saying.
Maximally
Supersymmetric.
What fields? String theories.
So let's say n equal to 4 superionicals
Yes.
coupled to massive high spin resonances, like coupled to n equal to 4 superionicals on the Coulomb branch. So we have scattering of massless external states with exchanges of massive high spins.
Okay.
So then also it will work. So
Why?
that I don't know.
What is the statement of entanglement here? Like, getting this.
Yeah.
I just explained this slide, yeah.
Right, yeah. Linear entropy is defined by this, where we have a density matrix formed out of this
So
state.
it's subspace,
Yeah,
it
yeah.
seems to be like a.
Initial and
It's a momentum space,
it's a helicity space.
helicity.
Yeah, in the helicity space.
Achha, so you are assuming scattering of
Gluons.
similar particles, gluons.
Gluon with different helicities.
That's it.
So this entanglement defined in the helicity space. Plus minus going to minus plus plus plus. So we will have 2 by 2 matrix. So
Okay, so you are looking at the change in entanglement.
yeah,
So
as we scatter.
as you said, so there's some change in entanglement that this quantity captures that.
Capture. Yeah. That's yeah. I mean, so this is just an observation and
And what is the second line? How does it get related to the?
right. And so okay. So claim is that this change will be captured because is P1 going to P1 P2 again will be captured. We will capture this scattering in the forward limit.
What? This is the question.
Okay. So I can show you the calculation details, but I do not have an offhand answer to justify.
What calculation? I mean, you like.
So yeah. So if we there's a calculation of how to compute this change in the linear entropies in this scattering process. Okay, because okay. The point is, how are the final states related to the initial state? Final states are related to t times the initial state. T is a transforming scattering amplitude. Okay, so from there we will get this thing, and it is a perturbative calculation, meaning. So this is looking at the linear order in the coupling constant. So then there will be PT dagger as well. So to the linear order, because of the conservation of momentum, a part is our calculation and part has appeared before in this paper by Aud, Chung, Wang, and also Aninda and his collaborators. They did a similar calculation, but in the color space of the pion scattering. But the helicity thing is more explored, I guess, in this paper, Aud, Chung, Wang, yes, it all this paper. So yeah, so here the final state is related to transfer matrix times initial state, and then we are calculating. Yeah, I can go into this, but this is roughly the idea.
Yeah, so this imaginary part of it enters to the transfer.
To the transfer matrix, exactly. So there's an identity part and then there's a transfer matrix.
But then once you conclude this delta E, it's not exactly delta E which is proportional to W naught, right? So you're saying some.
Yeah, so this one is actually proportional to W naught now. Yeah.
Then what is the ES?
So they are full. So amplitude, since we can color Gluon scattering, amplitude has this form factor and the tensor structure. So this yeah. So that will give S square times something. Okay, so do I need to stop right now, or I can just explain?
So,
Yeah.
Time?
Not stop.
7 minutes.
Okay. So let me quickly explain the closed string then. Okay. So this is a representation of the closed string. So, and when we mean closed string, we are only looking at the form factor. The tensor structure will contribute a factor of S equals 4. So it's the expansion or is the representation of the form factor. So I think the question about blue one will come when we include the tensor structure S4 here as well. And this is the fully Gaussian symmetric representation of S1, S2, and S3 there. And it satisfies the constraint that S1 plus S2 plus S3 equal to 0. Therefore, we have this plus minus. Okay, so eventually we'll have this plus minus sign, and then when you take the product of these Pochhammers, they actually become square. It's slightly non-trivial. They become square, and although there are square roots, if we actually open these squares, they become nothing but the polynomials at the residue. So there are no additional singularities. And so again, this can be used to do a bootstrap approach. This is a more unrefined version of this, where the CLs are not fixed. But here, if we fix the CLs, or this is literally this expansion. And then there are some curious features so this was the residue or the polynomial part appearing in the closed string, and on the residue this actually becomes square of the open string, which is kind of expected also. And then what we can do is do a low energy expansion of the things on both the sides. So for the double copier, it's called KLT kernel. It can be also interpreted as inverse of some pi cube amplitude kind of thing. So we have two copies of the open string with a kernel, and what we are doing here is a low energy expansion around S1 equal to 0, S2 equal to 0, and we obtain this. So this is the first thing, which goes as 1 by S cube thing. And then at the next order, that is 1 by S1 order, we obtain a term like this. Now, this actually manifestly violates the full crossing symmetry. So this has to be better. This better be 0. And in fact, so when we do the low energy expansion, we know this W00 for the open string, which is nothing but minus pi square by 2, pi square by 6, this zeta 2. So if we add over these things, they actually become this zeta function. And so other orders are, so the idea is that, so this is not something that we have finished, but the idea is that if we want to do a bootstrap using double copy, we can specify the Wilson coefficient such that all these non-crossing symmetric terms are cancelled. And that actually gives us some new representations of zeta functions as well. So this is zeta 2 and this is zeta 3. All of that then contain this free parameter lambda, and they are quite well converging things. In fact, well converging series. In fact, we have a generating function, and from there we can find the zeta functions using these Stirling's numbers and Jacobi polynomials, and they are like quite. So these are zeta functions for positive integer arguments. Okay, so okay, this is something I want to share. Like we are currently working on this, and any kind of feedback will be very useful. So, do I need to go? Like stop?
5 minutes.
Okay, fine. So basically, some idea how to go beyond the 4 point. If as I mentioned earlier, that for bootstrap to get string uniquely, either we have to look at higher loops or at higher points. So first we have to develop the machinery to deal with higher points. So at 5 point, first of all, any kind of partial wave expansion is not known because we do not even know any analytic structure of the amplitude beyond the 4 point. I mean, very little knowledge. So what we can do is that 5 point requires 5 variables to be specified. Just like 4 point requires 2 variables, 5 point requires 5 variables. So 5 of them can be like any 5 Mandelstam variables. And for a very specific case, we are just looking at this ordering of the external states only. Okay. So then what we can have is, so in case of 4 point, what we can do is we can fix the center of mass energy and the angle between the two frames. So we have a little group frame, little group of the massive particles which are being exchanged. We can go to that frame. Then what we will have is center of mass energy and T channel, which can be expressed in terms of some theta angles. So this theta actually comes from matching two little group frames, two center of mass frames, which involve some little group transformation parameters. In the 4 point case, there was 1, but in the 5 point case, actually, we can go to 3 center of mass frames like this. And then the question is how many least number of parameters we need to specify to explain the kinematics, and it so turns out that we need to specify 3 angles. So these 3 angles are, so these are like center of mass frames. We can go from one frame, we can do a rotation here, we can do a rotation here from here to here or here to here. And overall, because these two rotations, these are along x-axis, they can, although this is one frame, but actually this is a center of mass frame. There are 2 center of mass frames involved. One is from looking at this side, one is looking at this side. So there is a boost also involved, and boost will be fixed by requiring momentum conservation. So then there will be an overall like angular rotation involved along this axis as well. So this gives us 3 parameters, and using these 3 parameters, and by looking at the unitary irreducible representations of this SOD in this case, we can write an expansion of this form. Now, this will be useful to do to take a first step towards a partial wave expansion. And these are given by in terms of associated Eigenbauer polynomials. So these are expansion, and what we checked is that like we took the residues of different amplitudes and calculated some of this, and then we checked that they actually converge. At least the residues over the poles summation that actually converge. And now to proceed further, we also need to specify what we mean by crossing symmetry in case of 5 point. And let's say the simplest example where we take this trace 5 cube theory and compute the 5 point color ordered amplitude. So this is the amplitude. And if we change, let's say S1 to S34, then this does not remain invariant. But simultaneously, we need to change this S51 and S45 for this to remain invariant. So this is a statement of crossing symmetry, and analogously, we'll have 4 more sets of double exchanges, which will restore or which will remain this amplitude invariant. So this
S1,
S12 are basically the Mandelstam variables. Earlier we are calling STU, and S12 is, so Sij is minus whole pi plus pj whole square. So S12 is minus of P1 plus P2 whole square.
P1 plus P2,
Whole square.
not the mod.
No, not the mod.
No,
No, not the mod. Exactly. P1 plus P2 whole, yeah. So there are like 5 such exchanges for double exchanges possible, and that is a statement of the cosmic symmetry. And in fact, this symmetry, as we checked, holds also for this 5-point tachyon scattering. Okay. So okay, I'll not not go in details. So in one dispersion relation that is known for 5-point case is hold 3 of the variables fixed and look at the double discontinuities of any 2 channels. The point is that if we have an amplitude like this, you see that the poles are, meaning we cannot have arbitrary set of poles. We cannot have a pole like S12 and S23. We cannot have, we have to have a pole like S12, S34, 2, 3, 4, 5. This computation. So therefore, we can look at double discontinuity at, let's say, S1 to S34 channel or S2, 3, S4, 5. So using that double discontinuity, we can write down a like a dispersion relation of this form. And for that, so this is the like discontinuity in S1 to S3, and this holds for this tachyon amplitude, which has this high energy behavior like this. So when you take S1 to S34 to infinity, the other the dependence on the other variables come through these exponents. And each of them have to be negative. And like exponents, S23 minus S45, these combinations have to be negative. And that does not actually mean that all of them individually have to be negative. Meaning there can be like S23 can be positive and others are negative, something like that. The reason I'm saying is that when you do a fixed T dispersion relations, we usually go away from the location of the poles in the T channel. We always keep T negative, but because of this arc at infinity behavior, because of this high energy behavior, we have more flexibility, and that's why that expansion actually works, the thing that I showed. Because otherwise, in this expansion, it is not guaranteed that the other variables will always remain negative for cos theta lying between -1 to +1. So that's why this expansion works, but we need more checks. So the point is to find out a dispersion relation. So this is not finished work. To find out dispersion relation, we need an analog of this thing, S2 prime. And the properties, again, if I recall, is that this thing has a fixed point. Fixed point meaning this S2 prime will not change with sigma for certain values. For example, if I said S1 equal to minus lambda or S2 equal to minus lambda, S2 prime always goes to minus lambda. So we require properties such that, so like earlier we expressed S2 prime in terms of S1 or sigma. Now we need solutions for S2, 3, 4, 5 and 5, 1 in terms of S1, 2 and S3, 4. And the thing that we can check is that, I mean, the requirement is that when we choose, so let's say S1, 2 and S3, 4 dummy variables are sigma tau. When you say sigma is equal to S1, 2, tau is equal to S3, 4, this will return back to the values S2 prime 2, 3. So those are the variables entering the dispersion relation. They will come back to original kinematic value. For example, here, if I choose sigma is equal to S1, you see that S2 prime becomes S2. And sigma equal to S1, S2 prime becomes S2. Because of this thing. So we require that property, and also they should have fixed points. Like for certain values of S1, 2, S3, 4, and so on, they should not change with sigma and tau. And so this is just an inspection that those criteria are satisfied if we have some combinations of equations of this form. So yeah, I just leave it here. So these are the Poisson symmetric combinations. Earlier, when we are saying x and y, x was S1 plus S2, y was S1, S2. So these are the analog of those variables in case of 5 point. So yeah, so I'll stop here. So we have like revisited, or we have come up with some new representations which are very well convergent. Use them in the bootstrap analysis, and we use certain programming like linear programming to obtain the numerical results. And so we obtained a class of solutions which are string amplitudes, but certainly we obtained other solutions as well. And we are unable to rule them out, just imposing these constraints at the level of T-level 4 point. We require to go beyond like 4 point. We need to look at higher points or develop higher loops. Now, higher loop string amplitudes are difficult to compute, therefore it's a more difficult task. So we can try to develop our higher point, and that's a necessity for developing higher point dispersion relations. That's talking. Thank you very much.
Questions?
One challenge in the literature, where it's that for higher point amplitudes, the integral representation where you just integrate over n minus decisions is
Yeah, you're talking
it
about
doesn't
wall
work
yeah.
in for physics.
Right, right.
So yeah, just a basic question. Are the expansions you're developing for higher points suitable to solve that problem?
So if I understand you correctly, so you're saying that there are vertex operators in vertex operators, and you can fix n minus because of C like SL3C, SL2C invariance in the world shape, right? That's how we get n minus 3 integrals.
Yeah, that's one of them. But I'm just saying that those integrals you get only converge when you go to unphysical ends.
Right. So similarly, the 4-point case also, the integral will converge only when S is less than 0, T is less than 0. So we have to do an analytic continuation to go to the physical amplitude. So that is even at the level of 4-point amplitude, right?
That's true, but I'm just saying gammas are easy to analytically continue. These higher integrals are not. So
Okay.
Is that an application?
Yeah, so I don't know the immediate answer because we here in this work here like trying to obtain more from the amplitude instead of going to the world sheet integrations. So yeah, because this integration, these dispersion relations will also hold for quantum filtering amplitudes where we do not have this world sheet integral of the form. So maybe I don't know, maybe they will be useful, like to look at the world sheet integrals and how to do analytic continuation to get to physical amplitude. And in this case, because here also number of integrals are same, n minus 3. In the dispersion relation, for 5 point, you still have 2 integrations over like 2 variables sigma tau, just like 5 point. So yeah, analytic continuation. Yeah, right now I'm not able to say because I also don't know like how to do that.
Where I can ask
Yes.
that question. So for the lambda dispersion relation, 4 points. So you can equivalently imagine a CFT million amplitude that will have the same
Right.
dispersion relation.
Yes.
Then does lambda have a physical interpretation for CFT?
Physical interpretation, yeah. So even for fixed lambda, like for analog of the fixed t in that, so because in the main bootstrap, those variables can also be thought of as some kind of Anderson variables. The cross ratios.
Yes.
So I think physically that will be, I mean, if we have a Lagrangian prescription in ADS, if we have a Lagrangian prescription, so then how the cross ratio, meaning how to obtain the full amplitude from the Lagrangian, the same ambiguity will be inherited in that case. So that will maybe some
holographic theories.
Holographic theories, yes. They'll be using some renormalization procedure also.
Oh, in terms of thumb rules, you can't get extra, right? Because
so when you say sum rules or these null constraints that are often used.
so it will get mapped to that.
It will get mapped to that, exactly. Because in this case also, so these del n del lambda equal to 0, some linear combinations, finite or infinite, are equivalent to imposing these null constraints. Because in the usual case, what you do is first write down fixed t and then try to make them crossing symmetric and impose the constraints. And this is equivalent to that. So they can map to each other.
So if you have no other questions, let's thank the speaker. Thank you for lunch.